When we began this unit, I mentioned that it was going to be sort of a hodgepodge. There are lots of different physical descriptions we can make about our universe that are periodic in nature, from the motion of the planets around the sun to my first instance, the pendulum, sort of the default periodic motion, as the pendulum swings from side to side, taking the same amount of time to complete each cycle. Today, I'm going to specifically investigate the periodic motion of the pendulum, and it's going to make it possible for me to do some interesting calculations. Along with simply doing the physics of the pendulum, I'm going to start off with a little bit of very important and interesting history that you may have already learned about in your Western civilization classes. I've already mentioned early in our course that there was a time that Galileo Galilei went to the top of the Tower of Pisa, perhaps an apocryphal story, we're not 100% sure. But from the top of the Leaning Tower of Pisa, he dropped objects of different masses and discovered that in free fall, they would strike the ground at the same time, which was a revelation for Galileo and for our science. To us, it makes perfect sense. When a thing falls under the influence of gravity, the force of gravity, which is the mass times g, is equal to the mass times the acceleration. The masses cancel. It's not mass dependent. Everything accelerates towards the center of the Earth when an acceleration near the surface of the Earth equal to 9.8 meters per second squared. But Galileo did that work when he was at Pisa, and that's not the only thing that happened. There's another famous story of Galileo being in a cathedral, this very cathedral here that I've shown on the left-hand side. He was in the cathedral and he was watching this, I'm inclined to call it a chandelier, they tend to call it a lamp, but this is hanging from the roof of the cathedral, and we could imagine ourselves in Galileo's place looking up and observing it. I wonder if you see across the top here, it's very difficult, but you can see a line in the upper right-hand corner of the image. That's because the main cable that supports the light is connected to a tether so it can be pulled to the side. It would be pulled to the side because it wouldn't have been electrical. When Galileo was sitting in the cathedral, it was 1583. It would have been filled with oil and lit and then released to the center of the cathedral again. Well, Galileo, sitting in a pew, I imagine, looked up and noticed that it was swinging from side to side. He did not have an iPhone. He did not have an Apple Watch. He used his own pulse to time the swinging of the cathedral, and certainly, or the lamp in the cathedral. He had a lot of time on his hands, so he collected enough data that he noticed that the time period didn't depend on how far the lamp was swinging. If it was swinging a very little bit, it would take the same amount of time, that is the same number of his pulses, to swing as it would take to complete a cycle when it was swinging more broadly. He discovered that the period of the motion of the lamp did not depend on the angle that it strayed from the vertical. So he went back to his school, which was the University of Pisa, and worked out all the physics that we're going to discuss today. And I'd like to mention, just as a little aside, he was 17 when he did this. Because science, it turns out, is a young person's game. When you're old, like I am, you simply go around talking about science. The actual discoveries are made by the young. The simple pendulum, what's so simple about it? Here, I have support at the top and a string from which I hang a mass, and I release it and it'll swing back and forth. The string has a length L, and I describe the displacement from the vertical in terms of an angle theta drawn here on the diagram. This is called a simple pendulum. But calling it simple is a few very particular requirements. First of all, in order to qualify as a simple pendulum, I'm going to demand that the string is massless, which of course it isn't. But I could choose to use a material that had a very small mass. For example, I might build my pendulum and use a fine thread that when balled up in my hand produced so little weight that I could hardly feel it. And also I need the string to be inextensible. That means I need the string to not be stretchy. I've already calculated the elastic energy, and it turns out that if a bit of string can be stretched a bit, it does store elastic energy, and I'm not going to include that in my pendulum physics. So I want to make sure that my string is massless and inextensible. I also am not going to pay any attention to air drag. I've already commented several times that air drag is difficult to manage mathematically. It would certainly require lots and lots of calculus, and I'd really rather not. So I'm going to assume that the air drag is small. The only thing I have to do to make sure that that's true is to make sure that my pendulum moves slowly. Because no matter how challenging the math of it, I think we realize that the air drag is proportional to the speed. As I move around the room, just talking to you, I don't really feel the resistance of air. But if I were to travel at a high velocity, that is when the air resistance becomes significant. So I'll have my pendulum move slowly, so there's very little air drag. Here's a particular mathematical distinction. In order for the pendulum to qualify as simple, I have to keep the angle small. That is, the angle has to be less than about 10 degrees. There's nothing particularly special about 10 degrees. It's more of a rule of thumb. I have to keep the angle smaller than 10 degrees, or approximately 0.2 radians. Can I not solve the pendulum problem if the angle is bigger? I can, but it requires huge amounts of mathematics. And we don't want to engage that at this point in our description of the universe. So we'll settle for small angles, no air drag, and a massless string. We'll also leave out the derivation that leads us to a fact that Galileo was aware of. The time period of a pendulum, which I give the symbol capital T, is equal to 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity near the Earth's surface, which I already know quite well is 9.8 meters per second squared. I can derive this equation from first principles, and I like to show my students where equations come from. But the fact of the matter is that actually proving this equation requires a bit of calculus that even Galileo didn't have. And so we'll leave that bit out, and I'll ask you to simply trust me. Later on, you'll be given an opportunity to experimentally verify that this is true. And so we'll take that over lots and lots of algebra. At any rate, you can tell by looking at this equation that the period of a simple pendulum does not depend on the mass of the pendulum. What I mean by that is, in the equation, the mass doesn't appear. I don't use the mass to calculate the time period of the pendulum. And honestly, that doesn't surprise me, because Galileo had already done the experiment where he dropped objects of different masses and discovered that they hit the ground at the same time. So the time was the same for different masses in free fall. And free fall is caused by the force of gravity. The details are a bit different, but a pendulum swings because of gravity. In the absence of gravity, a pendulum wouldn't even hang, let alone swing back and forth. Because the pendulum motion depends on gravity, and Newton's second law has the mass times the acceleration in, if we were to do all that math, we would discover that once again the masses cancel, and the time period of the simple pendulum does not depend on the mass of the pendulum, in the same way that the free fall time does not depend on mass. Also, conspicuously absent from my time period of the pendulum is the angle. The period of the pendulum doesn't depend on the angle, which is only true if I let the angle be small. So it's only true in approximation, but it doesn't depend on the angle. What does it actually depend on? Well, 2 pi is a constant. So that's the same for any simple pendulum that I would choose to build. It depends only on the length of the pendulum and what planet you're on. So now I can build a pendulum and have a prediction for what the time period is, and maybe I would build an apparatus and give it a few swings and find out what the time period is experimentally. Here's a little observation about this equation and a little foray into something that I find that students of physics really don't enjoy, which is proportional reasoning. But before I get into that, I've done something sort of cute with my equation here. Sure, the time period of the pendulum is equal to 2 pi times the square root of L over G, 100%. But there's a funny little thing that's going on here, which is 100% a coincidence. There is no fundamental nature to this at all, But it turns out that the square root of g, which is the square root of 9.8, is equal to 3.13. The square root of g is 3.13. Pi, as you know, quite famously, is 3.14, which means pi divided by the square root of g is very nearly 1. And so in approximation, I can leave it out. I can leave it out of the equation and say that the time period of a pendulum is approximately equal to 2 times the square root of L. I didn't really state that for educational purposes. It's just a bit of fun with numbers. Yeah, so, I was just about to come to this. This sign here with the squiggles means approximately equal to. And now down here I'm stating that if I leave the 2 out, the time period is proportional to, which is what this symbol stands for. It looks like the Greek letter alpha, but it actually has a different shape than alpha. The time period is proportional to the square root of L. And this brings me to my point about proportional reasoning. What would happen if I increased the length of the pendulum by a factor of 4? Well, since the length of the pendulum appears in the numerator of the equation, if I increase the length of the pendulum, quite obviously, that's going to increase the time period of the motion. But consider this in the proportionality. If I put a factor of 4 under the radical next to the L, that 4 also obeys the square root. The square root of 4, of course, is 2, making things easy on us. So what I discover is that the square root of 4L is equal to 2 times the square root of L. And so the time period increases by a factor of 2 because of the square root. Increasing the length of the pendulum by a factor of 4 increases the period of the pendulum by a factor of 2. I can look at proportional reasoning the other way around as well and ask, what would I have to do to increase the period by a factor of 4? Well, looking at it this way, 4 times t, how am I going to get a factor of 4 on the right-hand side of my proportion? Well, I would need something the square root of which was 4. So 4 squared is 16. And I discovered that to increase the period by a factor of 4, I would have to increase the length of the pendulum by a factor of 16. We're going to encounter some of this proportional reasoning in our practice, and as our course goes on, quite a bit more proportional reasoning as we go. Here's my equation for the time period of a pendulum. I'm going to do a little bit of algebra to it, if you don't mind, and solve it for the length, just in case I have some questions in the future about calculating the length of a pendulum that would have a particular time period. My first step is to take the 2 pi here and all at once divide it to the other side of the equation so that the time period divided by 2 pi is equal to the square root of the length of the pendulum divided by g. Well, in order to get rid of the radical that still appears on the right-hand side of the equation, I'm going to square both sides of the equation, which requires that I square everything on the left-hand side. So the time squared, 2 squared is 4, and then the pi, also squared, is equal to, the radical vanishes on the right-hand side, L over g. Now I only have to multiply the g to the other side of the equation, and I get the same period of pendulum equation, except rearranged to solve for the length of the pendulum, which is the acceleration due to gravity divided by 4 pi squared times t squared. Just for an example calculation off the top of my head, I wondered, how long would a pendulum have to be such that when I set it oscillating at a small angle, its time period would be 1 second? I'm imagining it's kind of like a clock. I pull it to the side and it does a cycle every second. Well, I'll use my newfangled equation, and it's very, very easy to calculate. For g, I'll use 9.8 meters per second squared because I'm interested in a little bit of precision here. Divided by 4 pi squared, there's no reason to break that down. I've got a pi in my calculator. And the time period, which I'm asking for a time period of 1 second, then squared. 1 squared is 1, of course. And this works out to 0.248 meters. Only about yay long. If I built a pendulum like that, it would take 1 second for it to swing to and fro in its motion. An example of calculating the length of a pendulum from its time period. So I might have this equation for the time period of a pendulum written in a margin somewhere, and I might have this algebra rearrangement written in a margin somewhere, so that I'm prepared to calculate anything that comes my way. I want to imagine that I do an experiment to measure the angle of the pendulum as a function of time. There's a fancy way that I can do that. I've got all kinds of clever equipment, including ultrasonic motion detectors, kind of like a radar gun for physics experiments, and I could swing a pendulum in the vicinity of it and measure the position of the pendulum as a function of time. But even if I don't have high-tech stuff, I could do something really cute, like I could have a kind of funnel filled with sand hanging from a chain, and I could swing it back and forth over a long strip of paper and slide the paper to the left at constant speed. And then the sand running out of the pendulum, oh no, the sand's leaking out of the pendulum. The pendulum is going to become less massive. Doesn't matter. Pendulum period doesn't depend on mass. The sand falls onto the paper and makes a graph that looks just like this. Whether I do it high-tech or low-tech, the graph of the angle as a function of time looks like this graph. And I put it here because I know that when you look at it, it looks familiar to you. It's a graph that you've seen before. Here, it starts at theta, the angle that I pull back to, and when I release it, it very rapidly returns to 0. That's the vertical position. And then swings past the vertical to an angle that I'm calling the negative angle, the angle on the opposite side of vertical. I can choose to name the angles that way. And then it goes back and forth periodically in time. This is what a graph of periodicity looks like, not just for the pendulum, but all periodic motion. My hope is that all of you will look at this graph and think trigonometry. My further hope is that you look at it and say, that's either a sine or a cosine. I can't remember which. Beyond that, to look at this graph and say, that's a cosine, without doing any fancy math leading up to it. My experimental observation of this behavior tells me that if I could somehow come up with an equation for the angle as a function of time, it would depend on the cosine of the angle. This kind of mathematics holds true not only for the simple pendulum, but for a mass on a spring, for the waves on the ocean, for the waves of sound in the air, for the waves of light, for the motion of the planets around the sun, and all periodic motion. Not only the periodic motion that we choose to study in this unit, but all periodic motion in the universe.